Okay, I'm going to get started. So this week, what is machine learning, right? So you can kind of think of machine learning in a few different ways. Number one, it's a subset of artificial intelligence, and that's why there's this field called deep learning, which is an even deeper subfield. But basically, the way to think about machine learning is you're looking at this data, and you're telling this model, hey, can you make any generalizations on this data, where if you get a new data that it's never seen before, it can apply those generalizations to that new data set and be able to have fairly good predictions. So that's like the main thing, is just how well can this model generalize on old data that it's had to be able to make good predictions on the new data that it sees. And this is like an official definition from this textbook, which I'll actually add that to the Discord because it's pretty good. But basically, it's talking about whether the computer can learn from experience, so over time, or through like the number of runs it does on the data set, to be able to have better performance on those tasks. So we're going to do a quick little exercise. So we're going to have you guys spot the difference between these two very, very similar things, a bike and a tree. So basically, do you guys have any ideas, as like humans, how do you guys typically classify the difference between a bike and a tree? So raise your hands. What differences do you see between a bike and a tree? And by the way, this is like very like stupid stuff. Like one of them is green, one of them isn't. Raise your hands. Yes.
I mean, there's defining characteristics between their shapes that we can basically split, like which one is which. One has two circles, one doesn't. One has like a root that branches out. The other one has like, it's more of a horizontal shape, certain things like that.
Yeah, that's really good. So you basically said that you can define it based on shape. So one of them has circles, one of them doesn't. Any other ideas for like the difference between a bike and a tree? Yes.
The colors are more contrasting. The bike is just red and black. The tree is various hues.
Yeah, that's a really good point. The colors are more contrasting. And then this is something actually in machine learning where you can take an image and then give it the RGB values. And then using those RGB values of the image, like of each pixel, you would put in those color values. You could make it tell the difference between, hey, like these RGB values, which is like red, green, blue, of the pixels are a lot more pigmented. So therefore it could be something versus it could be something else. Okay, let's get one more and then I'll move on to the next slide. Difference between a bike and a tree. Like, you guys should not be getting stumped by this. If I pull up with a bike, are you guys going to be like, what are you doing at that tree? No, I'm just kidding. Okay, yeah. Yeah.
They're probably surrounded by different things. The bike would probably have the first color. The tree would probably be around.
Yeah, that's a really good point. So in like machine learning, a lot of times you look at the background. So then maybe that could be another thing of like, if this bike is being surrounded by a lot of nature, would the model just classify it as a tree just because it sees that? Or would it not? So yeah, those are all really great points, talking about shapes, etc. Now, how would you guys think like a machine learning model could classify the difference between a bike and a tree? Like what factors would help a computer be able to tell the difference? Like, hey, this is a bike versus, hey, this is a tree. Yeah. Perfect. So looking at other examples of bikes and other examples of trees, and maybe feeding that into a model and having it make predictions. Yeah, that's perfect. Any other things? I'll take one more. Oh, yeah.
I think I also recently did a project on something like this. How much, if these are images, then how much of pixels fill in the empty space? So in this case, the bike isn't taking up much space because the wheels are hollow and just a hollow little thin frame. The tree is it's filling up the space more, so that the one way computers can tell the difference.
Yeah, that's a great point. So one of these things fills up a lot of space, like a tree fills up a lot of space with its like branches and leaves, and a bike has like a lot of holes in it. So yeah, those are all great points. And yeah, that's basically the things that you put into a model, like these different things you guys are talking about between like the shapes, the spaces, and the colors. These things can all be called something that is called features. Yeah, so features are basically these things that we put into models, and we have the model determine based on those features if something is something or something else, if it's a classification task, or you can also have it predict something if it's a regression task. So if we go back to our exercise of training the computer to tell the difference between two things, a tree and a bicycle, how could we tell the machine learning model to make this prediction, right? So I hopefully think this is right. bright enough, but basically, here's a simple table that helps us lay out the data. So let's say we have two features, right? We have the feature has leaves, and we have the feature has wheels. We could model this data through a binary classification thing where we have, okay, the bike, no, does not have leaves, and the bike does have wheels. Or we can model it through the tree, yes, having leaves, and not having wheels. So as a human, this seems obvious, right? Like trees obviously have wheels, bikes obviously have, trees obviously have leaves, bikes obviously have wheels. But to a computer, this is valuable information to feed this information and put it into the structure. So this is like the step one of machine learning, is identifying this data and putting it into a format that the model can understand it in. And let's take this one step further, because for a computer, if you tell a computer yes or no, it's not going to be able to tell what that yes means or what that no means. So in this example, we can use something called binary classification, where if something is true, we represent it by using a 1, and if something isn't true, then we represent it by using a 0. So instead of writing yes or no, you can convert that data into a numeric format of like 1s or 0s, and this gives us something that we can use in matrix algebra, where we can use this to kind of examine how models work under the hood. And it's this kind of data and this kind of like features, which is called a feature matrix. So now that we've got our data nicely structured as a format that we can feed into our model, what can a computer do with this data? And this is where models come in. Machine learning models take this kind of data and try and find patterns so they can make predictions about new and unseen examples. So first off, we're going to talk about supervised learning. Supervised learning is a type of machine learning where we train a model on labeled data, i.e. we already know the answers. And the goal is for the model to learn the relationships between the inputs and between the outputs by learning that mapping. So you can think of it as teaching a student with flashcards, right? Like if you show it a flashcard of a tree and you give it that labeled tree, and if you show it a flashcard of a bicycle and you give it that labeled bicycle, then they learn to associate those pictures with those labels. And okay, I'm not sure why this isn't showing up, but supervised learning is a type of machine learning where each model is trained on that labeled data set, so you are giving this data to the model with those labels in the first place. And this also means that every single training example in your data is paired with an output label. So, for example, you can think of it as like, there could be something like that's like a one-to-one mapping, but you can even have a mapping where you have multiple inputs being mapped to one output as well. And the main two types of supervised learning we're going to be covering today is classification and regression. So first I want to quickly show you guys a quick meme of supervised learning versus unsupervised learning. So here you can see this person is showing apples to a robot, and the robot is just telling it no or yes. That's like binary. Or with unsupervised learning, which I'm going to cover later, basically you throw it a bunch of things, like all these apples and all these pictures of bananas, and then you're not telling it the label of, hey, this is an apple, hey, this is a banana. But what unsupervised learning does is it takes those two images and it tries to cluster all that data into these features. And it tries to plot all these features. For example, maybe it's plotting like colors, maybe it's plotting shapes, etc. And then based on those clusters of those inputs, it tries to kind of determine what the difference is between those two pictures to be able to classify it. So basically, supervised learning is labeled data where you're telling it what the output should be. Unsupervised learning is you're throwing in a bunch of data, you're not giving it any labels, and you're telling it, hey, based on this data, figure out some features where you can cluster this so we can distinguish this essentially. So let's get into regression versus classification. So this is where models come in, right? So machine learning models will take this type of data and try to find patterns so they can make predictions about new, unseen examples. So let's talk about regression, right? So the goal of regression is you want to be predicting a continuous value based on the inputs that you take in. And there's a lot of different use cases for this. So what are some use cases you guys can think of that a machine learning model could do where they're trying to predict one continuous output value? And I can start. So one thing could be with like real estate is if you have like the house information, like the square footage, the location, etc., you could have it predict, hey, what should a house price be? Any other examples that you guys can think of a continuous output and predicting that from linear inputs? Yeah.
Like stock values?
Yeah, stock values, perfect. Yeah, this is like a super good machine learning model example because it's very hard to predict, and like, you know, you can see recently the stock market crashed, right? So how many models are able to predict that? But basically, you can look at like the dips and the trends and correlate with those with other things. And if you guys can make a machine learning model that could predict the stock market, you guys get very rich. So you guys go for that. But yeah, basically, linear regression, which I'm talking on this slide as one of the examples, that is one of the most fundamental algorithms in regression because it models the relationship between those input features, which are represented as x's, and those output features, which are represented by y's, by a straight line. So it'll basically plot all these data points with like the x's and y's, where x's are inputs, y's are outputs. So inputs in this case could be has leaves or has wheels, and the outputs is tree or bike. And it basically plots all of these onto a graph, and then it tries to fit a line onto that graph to model that relationship between the two features. And here is the equation for a linear regression model. Basically, it's your classic y equals mx plus b, but essentially what's going on here is you have that y hat, which is the target output, and you are putting in all those inputs, which are x's, and you're weighting those x's based on how important they are to predict it. For example, for a house, right? Maybe if you have all those features like square footage and square footage or location, those things might have a higher weight in your linear regression model because maybe those things are more important. But there could be other features that are less important, like maybe the color of the house doesn't matter that much, right? So you put in those input features and you're weighting it with those weights, and that's how you get the line. So yeah, if I was going to draw a linear regression graph, does someone want to give me like a classification task or something? Or does someone want to give me like an input feature and an output feature? You can just think of something random, like a plan. Yeah.
GPA to how many hours you studied?
Oh, perfect. Okay, let's do that then. I'll see if I can pull up this thing. This is my first time drawing. Okay, so let's say you have this linear regression graph, right? So I am using my computer, but essentially on this left side, you're going to have the y hat, and on this x-axis, you're going to have all the x input points. So essentially what you're trying to do here is you're trying to predict GPA based on hours slept. So you could have each of these points on the x graph be hours slept. So let's say you're starting from, okay, who thinks they slept the least today? Raise your hand. Or you were among the least hours rested. Okay, who slept for 4 hours today? 5 hours? Okay, 5 hours. Okay, no, get more sleep, but let me write that down. So 5 hours, and then who thinks that they slept the most today? Who slept for like 12 hours? 11 hours? 10? 10, okay, awesome, okay, that's good. Let's write that down. 10, and actually that works out perfectly because I think I have 5 tick marks. So, if you guys have a graph, right, on the x-axis you're taking in that one input feature of how many hours you slept. So that could be 5 to 10, and these are your like x-axis labels. And in this case, we're doing this mapping one-to-one. So we're only taking in one input feature and we're getting one output feature. But in more complicated models, you would have multiple input features. So we have 5 to 10 hours, and then on this y-axis we have GPA, right? So let's say we put a few points. So what's a GPA that you guys, or maybe you guys raise your hands and just list out some random GPAs, and I'll plot them on this graph. So yeah.
2.5.
3.5. Okay. So let me just have this be 1, 2, 3. So 3.5. Let's say someone who's slept 5 hours of sleep has a 3.5 GPA. And then someone else want to list down GPA? 2. Okay. Let's say someone who slept for 7 hours has a 2 GPA. Does someone else want to say a GPA? 4.0? Okay. Let's say someone else who slept for 10 hours has a 4.0 GPA. So I'm going to add a few more points around this area, right? So we're going to have like these random points, and these are basically in this data science study that we're conducting right now. These are going to be points of GPA. So it's going to model people's inputs of how many hours of sleep they got, as well as outputs. And I'm kind of skewing this a little bit just so I can show the result of linear regression, but essentially what would happen is with the linear regression model, you would tell it, hey, find a line that fits these points the most, where if you plot the line on the model, and if you plot like the arrow between the point of the person's data on what their GPA is and how much they slept, and you're calculating that distance between your predicted line and that point, all of those distances would have the least distance possible. So basically, in this example, in my skewed data set, I would have like, oh, okay, that's kind of bad. I'll do this one. You can have a line like that, and it's a little bit high, but that would kind of be plotting the line of the model. And as you can see, it doesn't really show all of the data points properly. Like we do have this 140 at 10 hours of sleep. But essentially, it basically shows the regression model, and it kind of has that as a prediction. So then in the future, if you have someone who has, let's say, 6 hours of sleep, you would basically go up to that point on the line, and you would say, hey, if you have 6 hours of sleep, you've gotten, this would probably be about a 3.7 GPA. So this is kind of an example of linear regression. It's very simple, but it's kind of showing when you have one point, you model out the line, and then that's kind of how you get your output. So let me get my mouse back, and then, yeah. So talking about regression now, what are some performance metrics? How can we measure if our regression model is working well? You guys can write this down in your notes, but the one that I'm going to focus on is the sum of squared errors, which is basically what I'm talking about is when you have that line and when you have all those points that are plotted, you're calculating the distance between your predicted point and that line, and then you're adding up those points over time and squaring them to get the minimum distance. And I'm going to talk about that a little bit more in the next slide. So in the meantime, I'll talk a little bit about the rest of the points that are on this slide. So we have mean squared error. And something that you guys might see if you guys have done data science before is they will talk about RMSE. Basically, this is just the mean squared error, and you're just taking the square root of that, and then that's kind of like your RMSE value. And there's also another thing called R squared score. So this is between the 0 to 1 range, where 1 is true and 0 is false. And basically, this shows how well your predictions approximate data, but essentially what it's saying is how well does your line, how well does your line tell, like how much does the line tell you about your data? So like, if you have a 0.72 R squared value, it's basically saying that your model can explain 72% of the variance of that data. So basically what you want is you want it to be 1, you want it to explain 100% of the data, but obviously if it was 1, maybe you're overfitting your model, which we'll talk about that later. So hopefully you guys have this in your notes. It'll also be in the slides in the Discord later. But basically talking a little bit more about regression or how the sum of squared errors works. So this is the technical definition. Basically what this is saying is you take the sum from the first point on your data set all the way to the nth point, which is like your last point in your data set. And then for every single point in your data set, you are looking at the y subscript I, and then that is your actual value. And you're subtracting that by the predicted value, or what the value of your model is, and then you're squaring it. Can anyone think of why we would want to square our predicted value versus the actual value in our data set before we add it to each other? Yeah. Yeah, perfect. To get rid of the negative values. Because what could happen is, let's go back to my slide, which hopefully still has the drawings. Never mind. But basically, oh, it does, okay. Oh, okay, I can't see it on my computer, but okay. So if you go back to this slide, right? So you see that there's some points below this line and there's some points above this line, right? If you just added these points together, and maybe this isn't like the best example, but if you just added the points together, you could just get that average squared error as being the same thing as that line, right? Because if you have a line, if you have points below it and points above it, if you're just adding up those errors, like those positive errors and those negative errors, you could get an error which is maybe very little because you're just adding those up together. But that's why if you have like a negative error, you want to be squaring it so it's still being counted as a positive error. And if you have a positive error, you're counting it as a positive error. So that way you're adding it up over time. So maybe to like make this more clear, if you have like negative errors and positive errors, you want to be making them all positive by squaring them. So that way you're adding up the total error over time and you're not subtracting from your error when you're adding up new errors. Does that make sense? Okay, I'm getting some nods, some confused looks. Message me on Discord later if you're confused. I can explain it better. But yeah, basically going back to regression, SSE, that's kind of the technical definition. And basically what's happening here is it's penalizing larger deviations more. So if you have one outlier that is really far from your predicted value, one of the issues maybe with regression is that it's going to penalize those deviations a lot more with those outliers, and it's going to say, hey, this is a really bad model. Maybe if you have like one really bad outlier, whereas maybe your model is good and you just have that outlier in your data set. And your goal here is to minimize the sum of squared errors. So that's your goal with linear regression, and this is also in the technical article. So if you guys want to read more about how you can minimize the sum of squared errors, just check that out on the website and ask any questions. But yeah, now let's move on to classification. So this is the other type of supervised learning. And basically the definition is you are categorizing items into these classes. So for example, if I told you, hey, predict if this picture is a cat or a dog, those would be your two categories. And you're telling it, hey, predict if it's in one of these two classes. Versus with a regression model, you're telling it to predict a continuous output value. So that would be something like, hey, what's your house price, A regression model could also be, how much do you think this is a cat? But I mean, probably would be better just to do classification. So can you guys think of some examples in the real world where classification would be a useful task? Raise your hands. Yeah. Yeah.
You can classify images of like cavities in your teeth. Like for example, my dentist has this cool software.
Yeah, that's super cool. So you can put your images of your teeth and tell it to a machine learning model, hey, can you classify if this is a cavity or if this isn't a cavity? Can anyone think of any more classification examples of where we might apply this? Yeah. Oh, perfect. Yeah, that was like one of the examples of like, yeah, classifying emails if it's spam or not. That's perfect. Okay, awesome. So yeah, those are some use cases. Basically, the way that this model works is you put in this function f, where y, which is like your output, is like a finite set of labels. So maybe this could be like 0 or 1 or your 2 classes, or you could have it as being multiple classes, like maybe dogs, cats, cheetahs, elephants, if you're classifying animals. But essentially the goal is to assign the correct class to each of your inputs. So for each of your inputs, like xi in your equation, you're trying to assign that to a correct class. And the way that you can kind of tell if your classification model is correct or is working well is by using accuracy, precision, and recall. So accuracy would basically take your number of total predictions that are correct and divide that by the number of total predictions. So I can try writing this on the whiteboard, but basically, let's see. Okay, so if you guys have seen this before, it's basically like a true positive, true negative, false positive, false negative kind of graph. So let's see here. So yeah, so let's say you have, this is like true, and this is false, and this is true, and this is false. Or actually, true, positive. Yeah. Okay, so basically, what accuracy does is it takes the number of true positives and it takes the number of false positives and it divides that by the total number of predictions. So it's like the number of correct predictions divided by the number of total predictions. The thing that precision does is it looks at the number of true positives and it divides that by the number of true positives and false positives. And the place where precision works well in is if the cost of false positives is high, like in spam detection in emails, if there's a lot of false positives that show up in that data set, you would want to use something like precision to do that classification or measure that. And then the last thing is recall, where you're taking the number of true positives and you're dividing that by true positives plus false negatives. And just to quickly explain, true positive is if you tell it, if the model says, hey, this is true, and that's positive, like that's correct, it is true. False positive is if the model is telling you that's false when it's positive, and like that's not good. And then true negative is if the model is saying that it's negative and that's true, and then false negative is if the model is saying that's false and that's negative. So basically what you want is you want to get true positives and true negatives. You want to avoid the false positives and false negatives. So yeah, recall is good if you're dealing with something like really serious like cancer. You really want to make sure that you are minimizing like the number of you want to make sure that you're getting all the positives. So that's when recall would be important. And one thing that's good with recall is that if there's a high recall, that means that you have a fewer chance of getting false negatives as well. So what do you guys think we would use for the bicycle versus tree example? Do you guys think we'd use regression? Raise your hands. No hands? Okay, wow. Do you guys think we should use classification? Raise your hands. Yeah, okay, awesome. One thing, this is kind of a trick question, because logistic regression can be used in classification, so you guys are all, no, I'm just kidding. But yeah, you could use classification for this model. But logistic regression is also a good choice because logistic regression is basically also used for classification problems, which is kind of confusing because it does have that title of being a regression thing. But essentially, if you look at this equation, what it does is it looks at the probability that the input belongs to a category, like zeros or ones. But for logistic regression, you usually use it for binary classification. So if you're classifying something where you have multiple classes, I would not use this. But if you're looking at something like, hey, is it a bike or is it a tree, you could use logistic regression. And just to explain this equation a little bit more so you guys understand what's going on here, W is the weight vector, so it's defining the importance of each weight in the feature of the input. B is the bias term, so it's kind of adjusting the overall output of the function. So if your function is generally higher, you just kind of add or subtract like a bias term. And then E is Euler's number, I don't know if I'm pronouncing that correctly, But essentially what that exponent does is it makes sure that your output is squeezed between a 1 or a 0. So that way your sigmoid function isn't returning something that is over a 1 or under a 0. Your output will be between those two numbers. And the key difference to understand about linear and logistic regression is that both methods start by calculating a linear combination of these features. But while linear regression outputs continuous values, logistic regression uses that sigmoid function to calculate those probabilities and then turn those values into probabilities and use that for classification tasks. So that's what's the difference between linear and logistic and what makes logistic regression kind of like a classification algorithm, despite having regression in its name. And yeah, you guys can read these slides, I think hopefully that's helpful. And then I also wanted to talk a little bit about decision trees. You can also use these for classification, and these are also kind of a very intuitive model, but essentially I think this is on your course website, but you could have something, basically the way that a decision tree works, just so I can backtrack a little bit, is that each node is asking you a question, right? So it could be something like, is it a mammal? And then depending on if it's yes or no, you go to another node on the next level of the decision tree. So for example, here it's saying if it is a mammal, then you go to that node that says does it have fur. And then if it does have fur, then you kind of say, hey, it's a dog. Or if it's a mammal and if it doesn't have fur, then it's a dolphin. So basically, the way that this works in a machine learning model is that you have each internal node that represents a decision based on a feature in your data set. And each leaf node represents a final classification for that outcome. So yeah, over here you can see that the depth of this tree is 3 because it has 1, 2, 3 questions. But yeah, essentially this is iterating through each feature. And you can read more about that. But now let's talk about unsupervised learning. So this is a type of machine learning that, as I was kind of talking about earlier, works without unlabeled data. So you're basically throwing all this data at the model and you're saying, hey, use these features and make a classification based on these features. And I'm not going to tell you if this is a cat or a dog. You're going to figure out which one of these data points is more similar to the others. So this is slightly confusing because we don't fully know what's happening, quote unquote, under the hood. The model is just kind of using those features to determine what's going on. So in supervised learning, again, we're using input-output pairs. So we're telling the model whenever we have an input, what the output is. And basically, unsupervised learning is when you're giving it unlabeled data. So the way that this usually works, you might be like, hey, Ari, how does this even work? How is it able to do this? So we can use something called clustering. So the way that clustering works is you're basically grouping similar data points to each other. And let's say you have a space, right? And in this space, you have all these input features. It's going to be plotting all those input features on some point in this space, depending on what input feature. So it's going to be plotting all those points depending on what input features it has. So let's say you're plotting a bunch of pictures of bikes, right? You're going to plot maybe color and maybe shape and size, and all those input features are going to maybe make it be plotted somewhere on that space. But if you plot a bunch of trees, then all of those trees points might be also in a similar cluster to each other in this space. And then that would allow the model to determine, hey, this is a bike and then this is a tree. So it's two different things. And you can also do something that's called dimensionality reduction, where you're using something called principal component analysis, where if you have a data set with a bunch of features and you're plotting all these features onto this space, PCA allows you to simplify the number of features that you're plotting and basically reduce the number of dimensions that you have in this space to make it more simple. So it would be really nice, right, if you could plot every single input feature and every single thing and have D number of dimensions based on having D number of input features. But principal component analysis allows you to reduce this number of features down, so that way it's more simple and your model is not that costly. And this is also useful for anomaly patterns. So let's say you're looking at that cavity example we talked about earlier, right? So if you have a bunch of pictures of cavities, you could plot those anomalies and say hey, if you have this anomaly of thing where these pictures all look the same, you probably have a cavity. And it's also useful in fraud systems, like we were talking about with the email example earlier. And yeah, this sigmoid function is just a reminder of what we saw earlier in logistic regression. While it's not directly used in unsupervised learning, it's here to contrast how supervised methods like classification output probabilities using functions like this, whereas unsupervised models don't use those types of labels. So next, let's talk about k-means clustering. So if you're hey, how do we cluster these data sets for unsupervised learning? We use this. So we begin by choosing a number of k, or the number of clusters you want. So let's say you have bikes and trees. You would have 2 clusters maybe, bikes and trees. And basically what happens is the algorithm is randomly placing k, what's called centroids, into your feature space. And each data point is assigned to the nearest centroid by forming k groups. And then after you've plotted all of those points onto the space, you're going to recalculate the centroids by taking the average between the center of your centroid and each of the points. And then this way, you're allowed to kind of group those points into those clusters. And the objective of k-means is to minimize what's called the within cluster of sum of squares, or simply keep as points as close as possible to the cluster. So basically, instead of having points that are plotted all over, right, and you can't make any sense of them, what k-means clustering is doing is it's helping draw those points into clusters, and this allows you to classify the model. And it's also important to note that k-means is assuming that your data points are going to be assuming like roughly like spherical and equally sized clusters, which can be tricky, right? So that's why you can use this thing that's called the elbow method to find a good k value for like the number of k clusters you should have, and plot that cost function over different k values depending on your data set. And overall, this is like a very quick, scalable kind of method, and it works really well in a lot of different practical scenarios as well, like in market segmentation, or if you're compressing image data based on grouping pixel colors. These are all points where k-means clustering works well. And I also have a thing showing that each data point in k-means clustering is represented by a vector of multiple features. So for this xi, right, let's say you have this xi being this image. Maybe x1 is representing, hey, this is the color of the image, x2 is representing, this is the shape of the image, and x3 is representing some other feature. So basically, each of these elements of your vectors is a different feature of that input variable, and you're plotting that input variable into the space, and then you're using k-means clustering to group all of those variables into clusters to allow yourself to classify it. Can anyone think of any other examples of where unsupervised learning might be good? You have some examples on the slides here, so you could just say one of these. But
Maybe like species classification?
yeah, awesome. Species classification. That's a great example because you could take. What do you guys think would be some input features of species classification that you could use for k-means clustering? Yeah. The weight of the animal, perfect, yeah. Because if you're classifying something like a turtle versus an elephant, one would be a lot more heavy versus like a turtle. Any other features that you guys think could be helpful? I'll take one more feature. Yeah.
You could use like genetic markers.
Use genetic markers? Yeah, perfect. So you could use the genetic markers of the animal to help classify them. So yeah, awesome. So basically, like let's say you're taking this example where you're doing species classification with k-means clustering. You would have maybe 2 dimensions, which one would be the weight, and then one would be the genetic markers. And then in that 2-dimensional space, you are calculating the distances between the points and the centroids of that cluster, and then that way you're able to kind of do that classification. And essentially, the way that you calculate the distances between the points of those centroids and those clusters is using the Euclidean distance formula. So essentially what this is doing is it's looking at that x1, which is basically that point, and it's calculating the distance between that and the center. And that's kind of how you are able to standardize this formula. So now, this is a really important concept in machine learning, so you guys should really pay attention for this. I feel like this is probably one of the most important things. It's called overfitting versus underfitting. So basically, if you have a machine learning model, right, you could have the graph on the left-hand side, which is underfitted, where you have all these points, and you just have this line on it, and it really doesn't tell you too much about the data. And as you can see, if maybe I plotted some more points onto this model, it might not be very well predicted by the underfitted model. And you could also have something that's balanced, where you can see that line is kind of following those points really nicely, and it follows the trajectory of that data. And then you could also have something that's called overfitting, where as you can see, the line is basically doing those sharp bounces between different points to make sure that it's capturing all the variance in the data. But the issue with overfitting is that if you have a model that's perfectly overfit to your training data, if you give it new testing data, it is likely going to do really badly because it has been overfit to the training data set to not be able to generalize patterns well enough to apply to the testing data set. So basically the way you can think of it is at the beginning of this lecture, I said that machine learning, the way that you kind of want to make it good is you want it to make generalizations on the test data set or on the trained data set that will be applied well and work well on the test data set. So if you make generalizations that are not too specific, then on the test data set, it's not going to have really good predictions. But if you make too good predictions on the trained data set, if your test data set is like a little bit different, if it doesn't exactly match what you have in your trained data set, it's not going to have good predictions. So one example of this could even be like the stock market example we had earlier, right? Because if you're perfectly following all those dips, and if something happens, like recently when the stock market crashed, then our model would probably be pretty bad because it is so used to, the trends and stuff like that from before, where it's just going to expect something similar to happen to what's happened before. So as you can see in the underfitting model, the model is way too simple to capture the underlying patterns. And what underfitting is it's an example of high bias. So basically this model is making really strong assumptions like, okay, all the data is linear. And those assumptions will cause it to consistently miss when it comes to new data and miss the mark. On the other hand, we have overfitting, which, as I said, is when the model is too complex, so it's not going to work well. And what overfitting has is it has low bias. That means that the model is very flexible and it doesn't assume too much. However, it has a lot of high variance, which means that, as you can see, its performance is swinging really wildly between like each of the new data points, and it does really poorly on new unseen data. The risk with overfitting is that you guys could look at this overfit model and then calculate the accuracy, and it could have really good accuracy, right? You could say, hey, my model has like a 97% accuracy, let's put this out into the real world. And then as soon as you get new test data, boom, your model's accuracy is gonna like plummet to like 80, 70%. So that's why you really wanna make sure that the degrees of which you're fitting your model to is correct. So that's where we kind of get this like Goldilocks thing, where we want to find the sweet spot between the risk of underfitting and overfitting. So as you can see over here, the polynomial degree of the first model is 1, right? So as you can see, the training error is 0.4, which is pretty bad, 40% error, and the generalization error is 0.42, which is also pretty bad. But essentially what this is happening is it's being underfit because it's trying to capture this relationship with just a straight line, so it's going to kind of miss the mark. And then as you can see on the right-hand side with the polynomial fit degree 20, it's capturing all of that new data, but if you put a new point into this model, it's not going to work out well. So while the training error is pretty low, it's 0.07, which, that's really good, this model would not be really applicable in the real world. So over here, our Goldilocks spot would be if you have a polynomial fit of degree 4. So if we have a line that has like raised to x4, and it's plotting this kind of distribution, that's kind of our sweet spot. That's kind of our sweet spot because while the training error is 0.14, which is higher than the 0.07 training error that we had with the degree 20 model, it is still going to perform better on new data than the other model would. So yeah, this is where we can maybe talk a little bit about bias variance trade-offs a little bit too, which basically what this is saying is that bias is the error of having incorrect assumptions in the learning algorithm, and then high bias leads to underfitting. And then variance is the error of being too sensitive from those small changes. So for each of those changes, it's super volatile. And high variance leads to overfitting. So that's something you guys can write down in your notes, is bias variance trade-off. And that's in the technical article too. And yeah, that's basically the end of my lecture. Let me see what time it is. Okay, we have 8 minutes. So we have plenty of time to do your Kahoot. So let me, oh yeah, applause please. I'm just kidding. Okay, thank you. Okay, I will move on to the Kahoot now. And then, as you guys can see, last week, the winners are going to get Hershey white chocolate candy. So, yeah.
One question. How do we do the synthesis question?
Yeah, so for the synthesis question, actually, let me maybe navigate to the website over here. Just to show you guys. Okay, so you guys can go to I2. Oh, maybe I'll just do add content. And then, yeah. Okay, so go to your course website, and then go to machine learning, right? And then over here, while you guys are scrolling down, you can go to here for your technical article. So read this article to get all the good technical stuff. And then as you're scrolling down this literacy track, if you guys are on the literacy track, you will see these synthesis questions. So let me zoom in. So here are all these synthesis questions. So basically, pick one of these questions to answer and put this into your Discord on Tuesday. And then for the technical thing, let me just double check. Okay. So if you're on the technical track, you still read this literacy article, like this is still good to like learn, but you don't have to. Oh, okay. Okay. Wait, could you go back on just so I can see? Okay. But basically for the technical track, you go into your technical article and there's synthesis questions in your PDF of that article. So just answer those. And all of those are due on Thursday, as well as the literacy track. All of your synthesis questions on that website are due on Thursday. But just put the answer to one of your synthesis questions in your TA channel on Tuesdays. The reason why we have this is just to make sure you guys are getting started on the homework earlier, so you're not cramming it for Thursday evening. So that's kind of like the reasoning for it. But make sure you guys get your synthesis question in the Discord channel on Tuesday, just because we do grade those. So, yeah. Any other questions that you guys have from the lecture? Yeah.
So the technical track doesn't have to do the
Technical track does have to do the synthesis questions, but the ones in the article. So I'll pull up the article real quick. And then, as you can see, let me see. Yeah, they're pretty far down. I think they're in a bubble, yes. Okay, so all the synthesis questions will be in this kind of blue bubble, and you guys can answer these. As you can see, we did talk about some square errors, so we can talk about that. Synthesis question answer for you right there. And then I think there's another bubble. Yeah. So just go through all these bubbles and answer the synthesis questions. And this is based on the reading. And if you have any issues with that, you can definitely ask me or your teams.